So the next speaker will be Hao-Lun and Shu-Chih. So they both submitted this abstract, and today Shu-Chih will present, and the talk will be about including observation error correlation for assimilating radar, radial wind, and its impact on heavy rainfall prediction. So the floor is yours. We're looking forward to the presentation.
Thank you. I'm Shu-Chih from Central University in Taiwan, and this work is mainly done by my former student, Hao-Lun. And before I start, I would like to thank our collaborators, Drs. Terasaki and Miyoshi from RIKEN, Japan. Okay, so in Taiwan, we actually have a quite dense radar observation network to observe the wind and hydrometers conditions for severe weather. And radar data assimilation has been an essential component of our convective-scale data assimilation. But now we are facing a challenge to predict the short-lived extreme heavy rainfall event. And the model needs to capture the rapidly developed small-scale feature of the strong convections. So we are trying to better use the high-resolution radar data to represent the local small-scale features of severe weather system. And previously, studies have shown that accounting for the inter-channel error correlation for satellite data assimilation can improve the forecast. And for radar data assimilation, the spatial error correlation is considered for assimilating the radial velocity, and several work have done in the variational system. And the results suggest that including correlated observation error can include more observation information, and particularly on the small scale characteristic. So these studies inspired our work and to include the horizontal observation error correlation and in our radar ensemble data assimilation system, and so that we can improve the convective-scale precipitation prediction. So just briefly introduce our system. Our radar data assimilation is based on the LTKF algorithm. We assimilate radial velocity and reflectivity of the radars in Taiwan, and we perform rapid analysis cycle that is every 15 minutes, and the model resolution is 3 kilometers, and we use R localization and superobbing the strategies. And so instead of using a diagonal observation error covariance, now we have to modify the observation error covariance. So the error covariance is decomposed into correlation matrix and the error standard deviation. And we would like to modify the error correlation matrix to include the error correlation of the radial velocity. And then later we need to inverse the observation error covariance. And the following previous studies, we estimate the observation error correlation using the Zorzius method, which is based on the innovation and residues. And we have constructed the error correlation using super observation with different resolution from 9 kilometers to 3 kilometers. What we identified is that the error correlation scaled for radial velocity is about 25 kilometers. This says that it is not appropriate to use the assumption of uncorrelated error for our current resolution of super observation, which is 5 kilometers. So based on this result, we choose the Markov function to represent the error correlation and modify the observation error correlation matrix. But during our implementation, we faced two issues. First is that the radial wind error covariance matrix may not be positive definite, and we do have some negative eigenvalues, and also the covariance may also be yield conditioned. So to deal with those issues, for the first issue, we adjusted the gradient updating method proposed by John and in 2013 to adjust the error correlation matrix. The concept is that given a non-positive definite correlation matrix C, we try to find a positive definite correlation C hat, such that the distance between the modified and the original matrix is minimum in a certain matrix norm. And for the second issued about the air condition covariance, we apply the reconditioning method following Western 2014 and Terasaki et al. 2020. And so the idea is that the diagonal elements of the arrow correlation matrix is slightly perturbed, and the amount of perturbation is estimated by the ratio between the maximum of the eigenvalue and the required condition number. And we have to know that it is actually very expensive to compute the maximum of the eigenvalue. So it's approximated with this formula using the information of the average of the non-diagonal component of the correlation matrix. So now let me just briefly introduce the case of this study. So this case is a heavy rainfall event in Taiwan. So you can see that in this figure, within 6 hours, the heavy rainfall is happened over the northern tip of Taiwan, and in 6 hours it exceeds 300 millimeters. And there are several important factors contributing to this heavy rainfall event, including a quasi-stationary Meiyue front hovering over northern Taiwan, and also warm and moist southwesterly flow brought in those air, and also the local barrier jet, that is the interaction with the topography. So for this event, there is actually strong multi-scale interaction. And we have to know that it is actually difficult to capture the intensity and the location of this heavy rainfall. So in the following, I'm going to show the result from two sets of the experiment. One set used the 5 kilometer super observation, and the other one used the 3 kilometer super observation. And for each set, we have experiment without and with the arrow correlation for assimilating radial velocity, and the refractivity is assimilated with the assumption of uncorrelated arrow. So first, let me show the increment for the observation for the radial velocity and the zonal wind at the last analysis cycle. So first, you can see that for the 4 experiment, in general, they have similar pattern of increment. But if you looked more carefully in detail, you can see that after we include the correlated arrow, we have more small scale correction in both the radial velocity and also the wind curve, the zonal wind. And for assimilating higher resolution data, which is 3 kilometer super observation, and we can see that we can produce the more small scale, the increment, compared to the one using lower resolution super observation. And actually, not only for the wind field, the impact can also be identified in the refractivity field. So here I'm showing you the 2-hour refractivity forecast. And so in this result, you can see that it's clear that only the experiment using the correlated arrow is able to have this east-west oriented rain band similar to the observation. And other experiments have unrealistic, this reversed V-shape refractivity. So this result suggests that by including the correlated arrow, we can better use the high resolution observation and extract more small scale information. So to emphasize this, we conduct FFT analysis to all the analysis increment and construct the mean power spectrum of them. So here I'm showing the result of the zonal wind increment. So it's clear that the one using the correlated arrow, which is indicated as a red line here, has more small scale, the increment, than the one using diagonal, the observation arrow covariance. And this could be understood by looking at their eigenspectrum. So if we are using the diagonal R, we have the same eigenvalues for different modes. But after the error correlation is included, the eigenvalue of these modes with smaller scales become smaller. So that means the observation error will be smaller at smaller scales, which give more weights to these observations. So, and not only the wind field, we also see that the impact can be identified in the moisture field. And here you can see that actually the impact on the moisture can be identified at all scaled. And this is because that after there are more scaled included, more scaled increment included in the wind field, actually we produce stronger convergence. And then those stronger convergence bringing more stronger the moisture correction. And this is the difference between the one using the correlated R and using the diagonal R. So you can see that the moisture, there's a very strong moisture enhancement, and this happened at where the heavy precipitation occurred. So this set up a more favorable condition for developing and maintenance of convection in the main front convergence zone. So finally, the big question is whether the heavy rainfall prediction can be improved. So this slide shows that the probability forecast, which is indicated as the color shading here, and compared with the observation, which is the magenta color contour here. So you can see that both the refractivity and the QPF with threshold of 50 millimeter or 100 millimeter results using the correlated R indeed increase the probability, and that means that and have a result better agreed with the observation. So that means that after the observation error, the correlated error is included, we increase the probability to generate strong convection and heavy rainfall at the right location. So you can see that, for example, this one, so you can see compared to the diagonal, the R, you can see the probability forecast increased, and even for this a much stronger heavy rain. So to justify the use of the adjusted gradient updating method, we conduct a sensitivity that simply remove the negative, the eigenvalues. So, and we call this eigen method. But after this is done, we see that there's the previous advantage that having small scale the increment actually is much less evident. And for the precipitation forecast, we also see that compared to the first one that using the adjusted gradient updating method, now using the eigen method, actually the precipitation forecast does not have a obvious advantage compared to the original one. So, and we think that the degraded performance may result from the reduction of the matrix rank because we remove the modes that has the negative, the eigenvalues. And before I close my talk, I would like to emphasize that we also performed an experiment that using different error correlations scaled, and we found that actually the length scale, the 25 kilometer, can best represent the precipitation event of this case. So to summarize today's talk, we include the error correlation in radar ensemble data assimilation system, but we have to deal with issues of non-positive definite and ill condition matrix issues. And we also see that if we can assimilate the radar radial velocity with the correlated error, and this can bring out the advantage of the high resolution radar data. And what we see is that we have more small scale correction lead to enhancement of local convergence and the moisture, which further improves the precipitation prediction. But with the sensitivity experiment, we show that actually it's important to keep the rank of the observation error correlation matrix And also a proper observation error correlation scale is critical to optimize the observation impact. Thank you very much.
Thank you very much, Shu-Chih, for this nice presentation. And we already have 2 questions in the YOPET. I will read the first one from Anna Shileva. How does R localization in the LATKF interact with spatial correlations in R? Is there a need in adjusting horizontal localization distances?
Yes, we, let me go to this slide. So for this one, so I think the question is, sorry, let me make sure about the question. Yeah, so originally we were using a diagonal observation error covariance, but now this error covariance is decomposed into a diagonal matrix with the error standard deviation and also the error correlation matrix. So we reconstruct this error correlation matrix. So this become a full match that we use. And then we use the Markov function to represent the error correlation and then put them into this C matrix here.
Okay, and do you change the localization when you account for that?
No, actually, we still apply localization. So
but it's the same localization scales that you use, so you do not adjust the width of the localization.
For the localization, actually, the localization is 12 kilometers. So we use both the error correlation and the R localization.
Okay, so let's move on to the second question by Peter Jan van Leuven. He noticed that the radial wind updates can have different signs between 3 and 5 kilometer experiments. So he asked, is it not just more structure in the 3 kilometer experiments? Can you explain that? So the change in the sign.
I think, yeah, yeah, I think you're asking about this figure. Yes, I think that mainly is the background actually is slightly different, and also and yeah, that's the first thing. And the second thing is that if we enlarge the part that that we have more small scale correction, so it's mainly here, mainly the front region. So you can see that actually the one using the 3 kilometer super observation introduced more information. So I think maybe the pattern, not only because of the different background, but also because now we also use more observation.
Okay, Peter Jan says thanks. So there's another question from him. He said, would it be more useful to estimate R to the power of -1 directly instead of estimating R?
Sorry, maybe I go through this part too quickly. Actually, we reconstruct the error correlation matrix, and then we inverse the error correlation matrix. So actually, indeed we. So I guess.
So he was wondering if it's better to directly estimate the inverse R matrix. Did you consider that?
That I haven't considered that, but that's an interesting question. Maybe give me some time to I'll think about that. Yeah.
Yeah, you can answer his question in the OPET later in written form if you want to. So take your time. So I think that's all. There are no more questions, so we can move on, and we are perfectly in the schedule.